This is the last chapter on queuing theory, and in this one we talk about mean value analysis. So mean value analysis, as I said, is exact calculation, and then so let's see. First of all, let's see how we can do exact. So we are going to assume, first we are going to start with open queuing networks, and I hope you remember the open and the closed ones. In the open queuing networks, and so it can be open queuing network can represent transaction processing systems such as airline reservation systems and banking systems and so on and so forth. Transactions arrival is not dependent upon the load, and the arrivals are modeled as a Poisson process. So right here we begin with the assumption. Poisson process means what? Exponential inter-arrival times. All right? And so mean arrival rate is lambda. Exact analysis of such systems assumptions. All devices in the systems can be modeled either as a fixed capacity center or delay center. So there are lots of assumptions in this whole thing. We already made one assumption, which was exponential IID. By the way, I didn't say IID. IID was the independent and identically distributed arrivals. And then we are assuming that there are only two kinds here, fixed capacity and delay. Then all the fixed capacity service center clearly follow this thing. R is equal to S times 1 plus QI. This is actually the Little's law. R is equal to N lambda, N is here, and this is the service time. Sorry. This is actually the one of the laws that we already discussed. R is equal to, I think this is one of the, this is actually the Little's law. Anyway, so on arrival, the ith job sees QI jobs ahead of it, and therefore it has to wait QI times XI, plus it has to get a service itself. So the total response time for the job at the ith device is SI times 1 plus QI. So there are many queues, and when the user comes in, the queue at the device I is QI, and therefore its response time would be 1 plus QI times SI. So the service is memory less. So now this particular thing that we wrote down, this is the thing that the authors of MVA wrote down, and actually this is very well used. But the thing is, this is assuming lots of things which cannot be tested. See, one of the things about the operational laws was that you can test them. The test was very simple, just input equal to output. But we didn't assume anything else. But here we are assuming memory less service. So we are assuming exponential distributed service times. And without memory less assumption, we also need to know the time the job currently in service has already consumed. Because if the job came in, and then it not only needs to know that there are 5 people ahead of it in the queue, it also needs to know the 5th person, how long it has been in the queue. Or the first person, actually, this being served. So now we are assuming job flow balance. Second assumption is make it job flow balance. So we can say something about the throughput. Throughput equal to the systems times VI, system throughput times VI of the ith device. And utilization of the ith device, we can say something about that. And that would be Xi times SI, which will be X times VI times SI. And X is lambda. So lambda times VI SI, which is DI. So lambda times VI. So Q length of the ith device, now from the previous formula, is Xi times Ri. Ri was Si plus 1i QI. So basically, given all this, after some manipulation, you get that QI equal to UI times 1 plus QI. Now you can solve for QI from these two sides, and you will get QI equal to UI upon 1 minus UI. This is like rho upon 1 minus rho. We have seen this before. And where we have seen this before? Rho upon 1 minus rho. That the Q equal to, expected Q length equal to rho upon 1 minus rho. Have you seen it before? Where? MM1Q, good. So in MM1Q, so this is basically same thing. We are assuming in exponential, we are assuming single server. We are assuming exponential arrivals. and we are assuming exponential service time. So this is an MM1 queue. By some going around and around and around, we found the formula QI equal to UI upon 1 minus UI. Okay, this could have been derived using that live birth death processes and things like that, but we derived it is some other way. So this is for MM1Q. So the mean performance, the device response time is SI upon 1 minus UI. Again, for MM1Q, we know that one, right? So this would have been 1 upon mu divided by 1 minus rho. And then the delay centers, at the delay centers, these formulas, this is for MM1Q. For the delay centers, actually, where the device time is fixed, the service time is fixed, yeah. You get QI is equal to RI, the response time is equal to the service time, and the QI is equal to, basically equal to the UI, utilization. So on a service, if the service center is 50% busy, then the Q length is 0.5, because otherwise it is either 0 or 1, right? So this is, so now based upon this, we can solve some of the open queuing networks. So this is an example of an open queuing network. Here the jobs comes in, they go to the CPU, with some probability they go back, with some probability they go to disk A, with some probability they go to disk B, and with some probability they go out. So let's say we observe it for 3600 seconds, and we find that 10,800 people came in, or jobs came in. CPU busy time was so much, disk A busy time was so much, and the disk C busy time was so much. So now we can calculate several things. First of all, number of visits to disk A. And actually this is also measured. Number of visits to disk A is 75,000, and number of visits to disk B is 86,000, but the job number is 10,000, okay? So we calculate, this is our measured value. Now from this we can calculate something. First of all, we can calculate, and you have to go back and forth between the two slides. I won't go because I have to stay here, but basically you can go back and see. System throughput can be easily calculated because 10,800 jobs are served in 3600 seconds, which is 1 hour. And therefore, the system throughput is 3 jobs per second. Visit to disk A, there were 75,000 visits from 10,000 jobs, and therefore the ratio is 7 visits per job. Visit to disk B is 86,000 divided by 10,000 is 8 visits per job. Visit to CPU would be 1 plus 7 and 8 because, whenever you go to disk B, you come back. Whenever you go to disk A, you come back. And once you go out. So 1 plus visits to disk A and disk B. So total 16 visits to the CPU. Total time at the CPU is from the busy time, 1700 seconds, divided by number of jobs. We can say each job takes 0.16 seconds. Similarly, at the disk, each job takes 0.14 seconds. Similarly, at disk B, each job takes 0.24 seconds. Now we know the visits and we know the total demand. We can calculate the service times. So DI upon VI. SCPU is equal to 0.16 is the total disk demand right here. DCPU 0.16 divided by VCPU, which is 16. So if you divide 0.16 by 16, you get per visit 0.101 seconds. Similarly, per visit for disk A is 0.02 seconds. Per visit for disk B is 0.03 seconds. So we just calculated there. Yeah. I'm saying, how do you know that? How do you know only one job goes out? Here, all the servers are single servers. And so only when something finishes, then they go out. If this was multiple servers, then it's quite possible that the 2 people could finish the job. But this is single server. So only one can go out. More than one can come in. Yeah, that is possible. There is some probability that more than one can come in. But get out is only one, right? Now, more than one coming in, basically based upon your exponential distribution, there is some probability that the time is zero. Rare probability. So that will happen. Now, okay, here's the thing though. It is also a rare probability, very small probability that the arrival time is zero and the service time is zero, and then you get out. Yeah, actually, okay, here's the thing. To be fair, if you go back to MM1Q, there is a probability distribution for everything, for response time, for waiting time, for service, and everything else. If you put into those formulas, you will get some probability for all the events that you're talking about. That means actually you're looking for a very rare event where there's zero, something being zero. So that two jobs are getting out. Thing is, there is only single server, right? MM1Q. So the probability of something being zero is what you have to calculate. And I think that would be probably zero, but I'm not going to go back and check it out right now. Okay, it's like if you have a normal distribution, what is the probability of something being minus infinity? Zero, right? So similarly here, when you have exponential distribution which goes from zero to infinity, what is the probability of something being zero? Is zero, right? You can put that number in the exponential formula and then figure it out. I'm not going to do that right now, but there is a formula, and you can figure out what is the probability of something being zero. All right, good. So we move on, and now given that we know the B's and UX's and so on and so forth, we can calculate the utilizations of the devices, and we can see that the B device is the bottleneck in this case. And then we can calculate the response times for each of the devices, and we can calculate the system response time by adding all of those. So we have actually repeated something very similar to the operational laws. But these are not operational. These are basically using exact formula. And then we can calculate the number of clients to 8. So previously, the number of clients was 6 client system for whatever reason, right? Now we are going to go to 8. And so the arrival rate will go up by a factor of 8 by 6, and you can do the calculations similarly. And then your conclusion would be that it will degrade by whatever number. So you can do the calculations for any number of users. Now the next question is, what if we use a cache with disk B so that we improve the response time by 50%? With a hit rate of 50% and increases CPU throughput by 30%. So now you have to, this is the kind of thing, the division decision you make. And so all you have to do is readjust all the service times. VB goes up to 40, only 4, because instead of 8 digits, only 4 go to the disk. Other 4 are satisfied from the cache. CPU widgets go up because the cache has to be handled by the CPU, and therefore the total CPU demand goes up to some number. And then so the total CPU demand, and then you calculate the widget per demand. So you can calculate SB again, and then you can calculate the new utilizations, and now you see that the disk B is no longer bottleneck. Now the bottleneck is what? Among these three, what is the bottleneck? CPU has become the bottleneck now, right? Anyway, with that, we can calculate the system response time and so on and so forth. And now the second thing is, if we use a cache for this B, the service, so basically the conclusion is that if we use the cache, the response time improved by 28%. This is lower than before. Before it was the response time was 6.76 seconds, and now it is response time is 1.013, and it was 1.406. 1.406. Oh, this is actually the old one, 6 users. With 6 users, 1.406, and now it is 1.016, 28% better. Similarly, what if question is, what if we have a lower cost per server with only one disk and direct all IOs to it? So now we don't want to have two disks, we want to have one disk. If you want to have one disk, the number of visits will go up to 15 because now nobody goes to disk B, there's no disk B. And the service time at disk A is same, and therefore the total demand changes, utilization changes, and now you can see what becomes the bottleneck. Disk A becomes the bottleneck. If you just have one disk, obviously that will become the bottleneck. And the response time will go up to 3.31 seconds. So by a factor of 2.35. Will go up by a factor. So such things you can do. And now again, I keep emphasizing that these are examples, but these apply to your systems, the system that you're working on. And you can answer many of these what if questions in your system by something similar to this. All right, that brings us to MVA. And MVA allows solving for closed queuing systems, closed queuing networks, in a manner similar to that used for open queuing networks. But it gives only the mean performance. So that's why it's called mean value analysis. It does not give you the variance. It does not give you the distributions. It just gives you the mean performance. And it is limited to fixed capacity centers. Delay centers can be used later, and load dependent services can be considered later. We will just do this for the fixed capacity center. Okay. And given a queuing networks, here's the key formula for mean value analysis. That, remember this formula, R equal to S times 1 plus QI. This was the formula we had used here before. Actually, when we said very beginning, we said R is equal to SI1 plus QI. So if we have N minus 1 users, and we have solved it somehow exactly for N minus 1 users, and we came up that the IF device will have the QI. So QI as a function of N minus 1. Now, this is the problem is that I have used here both parentheses for both as a function and as a product, as its expression. So I should probably fix that. But here, QI is a function of N minus 1 and SI times this expression. Right? I will have to fix that. But Ri as a function of N. Right? Equal to Si, which is not a function of N, times 1 plus Qi function of N minus 1. So if we know the Q at N minus 1, then we can find out the response time with one more user. The new user comes into this device. It has to wait for the previous jobs to finish, and it has to service itself. And so the total response time, now this is based upon certain assumptions. First assumption is memory less, we talked about before, right? And so based upon that, if you assume that, then this formula is good. And then the good thing is that we can use this formula many, many times, starting with N equal to 0. N equal to 0 means no users, and just one user comes in, we can calculate the performance for that. Then we can bring the second user, and we can calculate the performance for that, and so on and so forth. We can keep doing it. And so we can calculate the performance for any users. Now, the thing is, this formula only gives you Ri. You can get the system throughput by adding all the Ri's. So if you have R1, R2, R3 at the device 1, 2, and 3, and the visits, you know, V1, V2, V3, you can just multiply V's and R's, and you get the total response time. If you know the total response time, you can calculate the total throughput. And once you know the total throughput, you can calculate the device throughput. Once you know the device throughput, then you can calculate the device queue length. So this is a cyclic thing. You start with the queue length, and you go back to the queue length. and so on and so forth. Okay, and the response time for delay centers is, you don't have to worry about n, because delay centers means like terminals. There is no queue. If there is no queue, then queue doesn't come. The response time remains equal to Si for all n's. And the good thing about queue is that queue is equal to 0. But when there is 0 user, there is 0 queue. So we can start with that. So we will do that one by one, okay, with these examples. Okay. So we are going to consider the same system as before. And here is what we know. Each user makes 10 IO requests to disk A and 5 requests to disk B. 10 and 5. So we wrote down here VA is equal to 10 and VB equal to 5. All right. And the service time per visit to disk A is 300 and 200 for disk B. So 300, we wrote down SA is equal to 0.3, SB is equal to 0.2. All right. We multiply those two to get DA equal to 3 and DB equal to 1. Then each request takes 2 seconds of CPU time and the user think time is 4 seconds. So we noted this down. What this means, dCPU equal to 2 and Z equal to 4. dCPU equal to 2, we know the visits to the CPU, which is equal to VA plus VB plus 1, 16. So we know SCPU is 0.125, basically 1 divided, this total 2 divided by 16 is 1/8. And Z is equal to 4 and N equal to 20. So we are given that all of this with 20 users. Somewhere we are given 20 users. Okay. So we can start with N equal to 0. If N equal to 0, then the Qs are equal to 0. Q CPU 0, QA 0, QB is equal to 0. Now the first user comes in. So we put one user and we can calculate the response time for that user. The formula is very simple. R is equal to S times 1 plus the previous Q. Previous Q is 0, and therefore for this first user, the response time at the CPU is simply 0.125 seconds. Because there was no Q, it came in. The response time per visit, by the way, is 0.125. Similarly, response time at the disk A would be 0.3. There is no Q, and it gets it. And at the disk B, it will be 0.2. But we have to multiply all this by the number of visits to get the total system response time. So it makes 16 digits to the CPU, 10 digits to the A, and 5 digits to B. So the total is 6 seconds. Even though there is no queue, the first user will take 6 seconds. Once we know the 6 seconds, we can calculate the system throughput. System throughput is equal to 1 upon 6 plus 4, R plus Z, is 0.1. Once we know 0.1, we can calculate the queue length. Queue length would be X times R CPU times B CPU. And so basically 0.1 times R CPU, which was calculated 1/8 before, times B CPU is 16, we get 0.2. Similarly, QA, the queue length with one user would be 0.3, and queue length with one user would be 0.1. So now we know the queue length with one user. Previously, with 0 users, the queue length was 0. First user came in, we calculate the response time, and we calculate the queue length. All right. Now that we know the queue length for one user, we can calculate everything else for 2 users now. So this is iterative thing, right? So with 2 users, when the second user comes in, it will have this thing. It will find that because of the first user, the queue length of the CPU is 0.2. All right. And therefore, its response time per visit would be 0.125 and 1 plus 0.2, which is 0.15. The response time at disk A would be 0.39. Response time at disk B would be 0.22. So using these queue lengths, we can calculate the response time for the second user. Actually, this will be for each of the 2 users. Now that they're both competing. And the system response time would be calculated. From the system response time, we can calculate the system throughput. From the system throughput, we can calculate the queue length again. Now we did it for 2, so we can do it for 3. And then for 500 and 501 and 502. So this is just an Excel worksheet. All right. And if you put this into Excel worksheet, what you do in Excel worksheet is you calculate the response time, you calculate the system throughput, and you calculate the queue length. From this row, you calculate the second row. From that row, you calculate the third row, and so on and so forth. And then you can plot as a function of number of users. You can calculate the system throughput. You can plot, it will come out like that. You can calculate the system response time as a function of this, and it comes out like that. Okay. Now, so you need to do practice. Basically, we'll do practice in a minute. But basically, so this is the whole summary. Summary of MVA is that you start with Q equal to 0 for all devices. Device 1 through N, Q is 0. And then for number of users, you do iteration for 1 equal to N. For each device, you calculate the news response time. Then you calculate the system response time, calculate the system throughput, calculate the new queue length, and then you go back. Okay. So I'm asking you to do this right here in the class, one line. Okay, this is a quiz. The four formulas are given here, so you don't have to go back and forth. Ri is equal to SIQI, R is equal to sigma of Ri Bi, X is equal to N upon Z plus R, and Q. Now here are the numbers. So you know what is SI, these numbers are given here. What is VI, these numbers are given, the digit numbers are given here. And Z is 5, and N you have to vary from 0 through whatever, right? So first write down for 0 users, fill in the blanks. For 0 users, you should be able to fill in the blanks. Once you know the 0 users, then fill in for 1 user. And remember, in these formulas, the Q is the previous row. R is this row. When you are filling out this row, you have to go for the Q on the next previous row, right? So first fill out the first row, and 0 row, and then when you calculate the first row, use the Q's from the previous row. Okay, it says in the bottom, fill in for N equal to 2. I think that requires a calculator, so you don't have to do that. Just do for N equal to 1, and then we can go through the answers. Anybody finished? One row. Rao, are you in the second row or what? Still the first row? Okay. Are you done with the first row? N equal to 1. Are you done with n equal to 1? Okay, n equal to 0 is easy. N equal to 0 is easy, right? Everybody did n equal to 0. That's easy. N equal to 1 is what we need. Because n equal to 0, you can see right here. Here's the answer. N equal to 0, everything is 0 here except r plus z, because z is not 0. So that would be r would be 0 and r plus z would be 5. And everything else is 0. Now, when you do n equal to 1, to calculate this thing, R CPU, you need this formula, S times 1 plus Q. Q is 0 here. So 1 plus Q is 1. And S is basically already written down right on the top. I wrote it down in the previous slide. S is 0.04. So here you will put 0.04. Then you will take 0.03 times 1 plus that, so on and so forth. So you will get 0.04, 0.03, same numbers here, and then calculating all this. Once you get up to this one here, Q's, and power was not required actually, so don't worry about the power. Last 0.15, then it will be done. Oh, because in the first row, yeah. So that's, see the first, okay, so that is, okay, good thing is that in these formulas that I have given you here, I should have put sub n here, right? Ri sub n equal to Si times 1 plus Qi n minus 1, right? So for when n equal to 0, there is no Qn minus 1, right? I mean, basically, we know that the Q is 0. So the first row is filled in with zeros. Si times, no, hold on. Yeah. The thing is, if you want to put 1 plus, then you have to put Q at the minus 1 users, which you don't have. So for the 0 users, the response time is 0. See, that's okay. So maybe that should be made clear. These formulas don't apply for 0 users. 0 user is initialization actually. Okay, so 0 users row is initialization. That you don't use any of these formulas. You just put response time is zeros, and therefore the total response time is 0. You multiply by all the V's, and then therefore the throughput is 0, and therefore the Q's are 0. With 0 users, this is initialization. Once you do that, the formulas come in only for the row 1. All right. Now you start using the formula, because here, then you will say Ri is equal to Si times 1 plus Qi, and the Qi is from the previous row. Then you do the R by multiplying Ri Vi. Now here you multiply these values. Then you get the total R. Then you get the total throughput, and then you calculate the Qi using this formula. So the first row is actually initialization. That one is just, if you know. And once you know this first row, then you can calculate the second row. But I would not ask you to do that in the class here, because that requires calculator and Excel worksheet, right? It can be done much easier. But you should just know how to program the first row. So you can program the first row and then copy the formula down onwards. All right. So there is homework that you will be doing at home. Let's just finish this. So MVA assumptions. MVA is applicable only if the network is a product farm network. And this means that the network should satisfy the condition job flow balance, one-step behavior, and device homogeneity. There are 3 assumptions. Job flow balance is nobody is killed. One-step behavior means one at a time. So that is what you were asking. What if somebody could, do 2 things at the same time? And device homogeneity. And homogeneity means basically the device, is doesn't really go through different kind of behaviors for different jobs. Also assume that all service centers are either fixed capacity service center, delay centers. We already talked about that. And we assume exponentially distributed time. So with all these assumptions, we can calculate the whole graph. And so that brings us to this homework, which is basically requires you to do an Excel worksheet up to 5 users. And that's the end of the lecture today, I think. Let's see. Maybe we can go to the next one. All right, so let's go to the next one. Any question about the MVA? That's the thing, before I go to the next one. Any question about MVA? Homework. In your Excel worksheet, first row you have to fill in by yourself, zeros. Second row you have to, which is number of users equal to 1, you have to program. All right? And program it in such a manner so that it uses the queues from the previous rows and then produces the new queues. And then program it in such a way so that you can copy the formula. And then copy it, and I copied it 50 times, but I'm asking you to do it 5 times. Okay? And then you get the whole thing. Yeah. This one? If you want to copy the row 2, you can copy it right now. Just to check your Excel worksheet. N equal to 2. You should get that answer in your Excel worksheet. This one? This one? This is power is throughput divided by response time. So throughput in this case is 0.149. Response time is 1.7. So the power is 0.14 divided by 1.7 is 0.08. So I'm doing this power to get this graph here. Just to find the V more clearly. You don't have to do power. Actually, the thing is, in the homework, I don't know whether I'm asking for power or not. I don't think so. But let's just see homework. Calculate the system throughput and response time. That's what I'm asking. System throughput and response time.